Hey guys, welcome back to UVM lecture series. In this video, let's see UVM Testbench code from the scratch for a D Flipflop design. We will be having a Testbench top. This Testbench top contains test as well as interface and DUT within this TB top. In the test, we will be having an environment. You can relate this with the block diagram. Within the environment, we will be having agent and we will be having a scoreboard. Within the agent, we will be having a sequencer, driver and monitor. This sequencer will be having a set of sequences, and sequence will be having a sequence item. So sequence item is the lower level block of the test bench and TB top is the highest level of the test bench. So let us understand all these by writing a code for the D flip-flop. So let us get into the editor. So here I have my D flip-flop design. Here you can see module DFF is the name of the module. I have taken clock, reset, D and Q as my input and output ports of D flip-flop. And my flip-flop is going to operate at the positive edge of the clock. The flip-flop output is sensitive at the positive edge of the clock. It means it is synchronous reset flip-flop. Means the reset and clock are synchronized here. Begin if reset is equal to 1, Q becomes 0. It means the reset is active high reset. Here I am using active high reset signal. So when reset becomes 1, Q will be 0. I am resetting the output of the D flip-flop to 0. Else Q will be following D. This is my design code. For that we need to write the test bench. Here I have testbench.sv. I am taking the time scale as 1 nanosecond per 1 nanosecond. So let me write the test bench top now. So module top, this is my name of the test bench top module. And first thing is that we need to include UVM underscore macros.svh file. So this .svh file is containing all the UVM macros we are going to use. And then we need to import the UVM package. Import UVM package : star. This contains all the UVM base classes. So then module top, and I am declaring the clock here. And then we need to instantiate the lower modules. So here for the top module, the lower modules are DUT as well as interface. So I am taking my DUT as DFF and clock, reset, D, Q are the components of DUT. And similarly, we have an interface. Let us look at the interface. So there is an interface between the DUT as well as test bench, I said. This interface is a type interface type. We need to declare it as a interface itself. Interface, I am giving the name as DFF underscore INTF. And here I need to pass the clock as an input to the interface. And other signals I am declaring it as logic. And here the clock generating from the top module is an input to the interface. That's why I am passing that clock over here. Okay. In the test bench, so I am declaring it as logic clock. Why? Because I need to generate it. And other signals the driver is going to give to the interface. From the interface we need to pass to the DUT. So DUT will be connected with the clock of the DUT will be connected with the interface clock. So here I have an DFF interface instance. The handle for this, that is INTF, the instance name, and I am passing this clock of the top module clock into the interface clock. Now I need to connect that INTF dot clock to the DUT clock. Okay, I hope this is clear. Now similarly, the reset signal is coming from the interface. So INTF dot RST I need to connect. I am connecting all the interface signals to the DUT now. INTF dot D is the input signal. Similarly, INTF dot Q. So all these reset D, Q signals will come from the sequencer to driver, then driver to the interface, then to D. That's why I am connecting all these through the interface. The clock signal which is generating from the top module itself, now we need to generate That clock signal I am giving it to interface, and through the interface only I am connecting. So let us generate the clock now. Initial, begin. Let me give clock is equal to 0 first, and then always for every 5 or 10 time minutes our clock will be clock is equal to not of clock. This is how I am generating. So no need of this begin. Initial clock is equal to 0, always # clock will be not of clock. So let me use a dollar monitor statement. Initial. So this is my top module of the test bench. So then let us go for interface. I have defined the interface in. So next let us go to the test. This is a class dff underscore test extends from the UVM test. Here UVM test is the base test class. This is the base test class of UVM. We are creating our test class. We are extending that from UVM test. And then as soon as you write the class, you need to register that class to a factory. This is register class to factory. We need to register the class to the UVM factory. There are many advantages registering this to the UVM factory. So the thing is that we need to use this macro tick UVM underscore component underscore utils. Here we need to pass the argument as the name of the class which we have created. By this way we can register our class which we have created to the factory. And remember, I am using UVM underscore component underscore utils here since test class is a component, UVM component. There are two UVM objects which are sequence item as well as sequence. Let us look at it further. And as soon as you register to the factory, let us write the standard constructor. The standard constructor is a function new. We need to pass the two things here. One is the name of the class, another one is the parent. Here string name is equal to dff underscore test is the name of the class which I have defined, comma UVM component parent. So this is the standard constructor. Then we need to write super.new and we need to pass name, comma parent. Here just I am using one UVM info statement which give you this string what I am going to write over here in the console or in the log. First we need to pass the ID. I am just naming it as test class. It means this display or the message is coming from the test class. That is just for the indication. We call it as ID. And this is velocity level. I am keeping it as UVM median. This is about DFF test component. Similarly, we need to create the environment. So let us create the environment component and the standard constructor. I am just copying the things here to make it simple. DFF underscore env is the name I am giving, and we need to extend that from the UVM env block. This is also a component, so we need to register to the factory with tick UVM component utils, and the name of this class is DFF env. And similarly, the standard constructor for this environment class is function new string name DFF env is the name, and UVM component is parent, and this remains same. Here I can change this to this is an environment class, and again I can take this thing to create the driver. This sequence class is not a component, this is an UVM object. So class DFF sequence, we need to pass to the factory registration macro, but here it is not a UVM component, so we need to register with UVM object utils. Okay, remember the difference. Sequence class is a object, so we need to declare that with the registration with the UVM object utils. Similarly, we need to write the standard constructor for the sequence object. Here we need to pass only the name. There will be no parent over here for the object. So there is no parent here also. And let me write, this is the sequence class. And then let us create sequence item .sv. I'm just changing it as sequence item, extending from UVM sequence item. So I have created all the components of the test bench. So let us save and try to run this test bench, and hopefully we are going to get the display for the clock signal. So for that I am selecting the Synopsys VCS simulator here, and no need to click on the EP wave. I am not displaying the waveform. So let us see. I am going to run this. So we are getting an error here, like source file cannot be opened. Source file UVM macros.svh cannot be opened for reading due to no such file directory. Why? Because here we need to select the test bench plus design as system verilog or verilog, and then we need to select UVM over here. Then only the simulator will read the code which I have written corresponds to UVM methodology. Then again save and try to run. So here we are getting one more error, like the module definition of the above instance is not found in the design. So here the interface which I have used DFF_INTF, we need to include over here. So let me include this stick. So let us run again. So this is running up to the maximum simulation time. So you can see here up to this time 5000 lines. So I have not used a $finish over here, so that's why it is keep on running. So let me define, after some 100 time minute we need to stop this simulation. So I am going to end after the 100 time minutes. So I am running again. Okay, now you can see at 0 time clock will be 0. We are starting with clock is equal to 0. For every time 10 time minutes clock will be not off clock. So you can see the clock generation is successful. Now test component. So if you look at the test bench architecture, we have TB top, that is a module, test, environment, agent, scoreboard, sequencer, driver, monitor are all classes, and interface is of type interface itself, and DUT is a module. So the test is a component. So I have written here test class is a UVM component. You can write it as UVM component. So these UVM components will be having phases. Sequence item and sequence are UVM objects. There will be no phases in objects. So let us start writing the build phase for the test component. So build phase. Build phase is a function void build_phase, and it will take the argument as UVM_phase. This is the syntax for the function. Let me write in function, and in between we are going to call the base class with super dot build phase, and we need to pass phase. So this is how the basic structure of a build phase function look like. And here in between in the function we need to create our lower modules. The test class consists of environment. Within the test we have env. So environment class is there over here. The name of the environment is dff_env. We need to instantiate that lower module and we need to give the handle. I am giving it as env. Now we need to create that component over here in the build phase. env is equal to dff_env is the class name. We need to use : type_id : creating an object. Here we need to pass again two arguments for this. One is env, this. So this is how we can create our lower module. We can create this environment which is come under the test using type id create method. So now let us move on to the next component, that is environment. You can see again the block diagram here. env consists of scoreboard and agent. So I have instantiated DFF agent and DFF scoreboard and I have given the handle as agent and SCB. We need to create those two under the build phase of environment now. So agent is equal to DFF agent using type id create method. We need to pass agent and this keyword. Similarly, SCB for the handle for the scoreboard, DFF scoreboard type id create method I am creating for this class. So this is under environment because of we have scoreboard and agent. Now let us move on to agent. Agent class consists of driver, monitor as well as sequencer. So we need to create driver, monitor and sequencer as having the handles drv, mon and sequencer, and I am creating those in the build phase. You can see over here. And then let us move on to driver. This driver is also a component. But if you look at the block diagram, here driver does not contain any lower module, right? Within the driver, is there any test bench component there? No. That's why in the build phase we are not going to create anything, right? But for the driver we require our sequence item class. We need to pass the name of the sequence item class. Why? Because this driver has to know which sequence item or the transaction we are going to pass from the sequencer to driver. And then comes monitor. Again, if you see the block diagram here, this monitor consists of no submodules. Monitor is standalone. So there is no other components over here for instantiation. And then comes sequencer. If you see sequencer here, this sequencer consists of sequence and sequence item, but this sequence and sequence item are not components, right? So here I am just passing the sequence item as an input to the sequencer, and then comes sequence. Sequence is a object. This is UVM object class. Okay. Since it is a UVM object class, there will be no phases. So we are not going to write any phases over here. This item is also a object class and there will be no phases. And then comes scoreboard. So this is also UVM component class. So within the scoreboard again there will be no submodules. So now comes the connect phase. What we do in connect phase? Connect phase is also a function. Function void connect phase. We need to pass UVM phase here, and super.connect phase of phase refers to the parent class connect phase. And here just I am printing a message as this is a test class connect phase and I am displaying it as connect phase, and the verbosity is UVM medium. So in the connect phase, what we are going to write here, connect the components. So in the build phase, what we did the creation of the lower components. In the connect phase, we are going to connect those components. If you look at the test bench architecture, within the test, what we have only environment. Do we have two lower modules? No. what environment consisting of? It consisting of scoreboard as well as agent. So there is a connection in between. Scoreboard and monitor are connected through an environment module. If you look at the environment, it has a connection in between scoreboard and monitor. We need to do this connection in environment, remember. Similarly, if you look at the agent, the lower component of agent is sequencer and driver. There is a connection we need to make in between sequencer and driver in a agent. So agent and environment will be having connect phases. Only agent and environment will be having connect phases. There is no need of any other connect phases needed in other test bench components of UVM. So let us jump on to agent first and let us connect driver and sequencer. So I have written here function void connect phase, UVM phase, and I am displaying a message as it is agent class and connect phase. Agent class is the ID for the UVM info and the message it is going to print is connect phase. So here what we are supposed to do, we need to connect the sequencer to driver. Why? Because the transactions will flow from sequencer to driver. So the sender is sequencer, the receiver is driver here. So we need to use the port here. Let me write here connecting driver sequencer using TLM ports. So transaction level modeling is the concept of UVM which provide the standard ports as sequence item port and sequence item export. So clearly observe here, the driver is going to receive. The driver will be having sequence item port. Yes, refers to the receiving port of the driver. Dot connect. Sequencer will be having sequence item export. Sequencer is exporting here. So what it is going to export? The transaction. The transaction is sequence item. Then comes the another connection between the scoreboard and monitor in environment block. So let us jump on to environment. In the environment, again the build phase is over. We have created agent and scoreboard. Now monitor and scoreboard connection we need to make. This monitor will be present inside the agent. So in the connect phase, let us write function connect phase. You can see here we need to connect monitor MON over here and SCB is my scoreboard. We need to connect here. How we need to connect? Monitor is not directly available in the environment. Monitor is present inside the agent. That's why agent is the handle I am going to use. Within the agent we will be having monitor. What is the name of that? MON. So here agent dot MON dot item collected port. Item collected port is the port of the monitor. Connect SCB. SCB is the handle of the scoreboard. Dot item collected export. We need to connect to the item collected export of the scoreboard to the item collected port of the agent. So this is about the connect phase. Connect phase will come only in the environment and agent. So far we have seen build phase and connect phase of the different UVM components. Once the DUT as well as interface is declared in the test bench top module, we need to set the interface into the config DB. So UVM configuration database allows us to set that interface in the top module first, and then the lower components can get that easily. So within the initial block, I am setting the UVM config DB here using UVM underscore config underscore DB. We need to pass the name of the interface, that is virtual DFF underscore INTF colon. We need to use the set method here to set the interface into the configuration database. Set, it takes 4 arguments. First one is null. You can also write UVM root over here. So then the second argument is star. This star allows the interface which you are going to set into the configuration database to get in all the lower components. That's why we are going to use star. Suppose we are setting this to particular component, then you can mention that over here. Then the third argument is VIF. VIF is the key for the configuration database. Using this key, the other lower components are going to get. And INTF is the INTF handle which I have used here in the declaration or instantiation of my interface. So once we set in the top module, we are going to get this interface in the driver and monitor class. In the driver class, you can see in the build phase, I am going to write get configuration database. UVM config DB virtual D under DFF underscore INTF. Here I am using get method. Get, where I am getting in this class, and VIF is the key which I have used while setting. INTF is the handle. And remember, in the driver and monitor, the interface is a virtual interface. The physical interface we can't use over here. Since it is a dynamic component, we need to use the virtual interface in the driver as well as in the monitor. So virtual DFF underscore INTF with the handle INTF. So I am passing that handle here. This is how we can get the interface in the driver from the configuration database. If the interface getting failed, we need to stop the simulation. That's why I am triggering UVM fatal here. You can also write UVM error, but better to write UVM fatal since this interface having all the signals of our DUT. So once we fail to get that in the driver itself, no further simulation will occur. That's why UVM fatal is used, and here we need to write the display message. And similarly in the monitor also I am defining my interface as virtual interface with INTF, and in the build phase I am going to get the interface handle from the configuration database. Again, if it fails, I am triggering UVM fatal. This is how we can set the interface from the top module, and we are trying to get in the driver and monitor. If it fails, we need to trigger the UVM fatal. Then let us move on to the other classes and see the next phases. In the connect phase, we are going to connect the lower components, but in the test will not be any connection made. So simply I have written the connect phase here. It is not required also. Next comes end of elaboration phase. This end of elaboration phase is going to give you the UVM hierarchy. You have defined all the lower components and how they are connected each other. What is the hierarchy of UVM that you can print using end of elaboration phase. So in the end of elaboration phase, I have used print method. This print method gives you the UVM hierarchy in your log, simulation log. Then comes the run phase. So run phase is a task. Run phase is always defined as a task. Why? Because this run phase is the heart of simulation. So run phase consumes much time. All the transactions flow will be in the run phase itself. So task run phase, UVM phase. Here we need to start our sequence. We need to start our sequence over here. SEQ is the sequence, DFF sequence. I am giving the handle as SEQ. That's why SEQ dot start. I am starting that sequence. On which sequencer we need to start? That's why environment agent sequencer. It means SEQR is the handle of my sequencer. It is not there over here. Sequencer present inside agent. So in the agent class, you can see sequencer is defined and the handle is SEQR. That's why here environment under that agent is there, under that sequencer is there. That's why I am giving the complete path since SEQR is not available in the test. This is how we can start our sequence. So before that, what we need to do to give a time to complete this sequence, we need to raise the objection phase.rise objection in this class. Stay in the run phase until the test dropping the objection. Means the simulation should be there in the run phase itself until this sequence get completed. Once it is completed, then drop the objection. That is what we are writing here, rise objection and drop objection. If you are not going to rise and drop the objection, simulation may get over in less time. Then coming to the next component, environment. In environment, we have connected the lower components, that is monitor and scoreboard using analysis ports. Here there is no requirement of run phase. Then comes driver. In the driver, run phase is very much required and it is very important phase. In the run phase of the driver, what we are going to do? Give the transaction which we are going to get into the DUT. That's fine. Here you can see sequence item port is the port of the driver, get the next item of the transaction. And after getting the next item from the port, we need to drive that. So how we are going to drive? This is the drive task I have written here. Otherwise, you can write all these in between the lines here also. So here is the drive task. What it will do? It will take the transaction. The transaction will be consisting of reset D as well as Q, and we are passing that to the interface handles. Interface reset, interface D and interface Q. This is how driver will give the transaction to the interface signal. And then from the sequence item port, we need to send the message as item done. So for this, we need to understand the communication between the sequence, sequencer and driver. You can see I am explaining driver. This driver will communicate with the sequencer as well as the sequence. So driver get the next item. It will request the sequence item from the sequencer. Sequencer will give that information to the sequence. The sequence will randomize and then they send the request to the sequencer, sending the sequence item to the driver. And driver then it gives to the DUT through the interface. And similarly, the response will be come from the DUT to the driver, and driver will send the item done information to the sequence. This is how the run phase of sequence, sequencer and driver works. So now in the sequence, if you look at the sequence, in the sequence we need to have our transaction, that is sequence item, and sequence is an object class, though there will be no phases. Here we need to write a task body task. This body task will do this functionality of the sequence. What it will do? First it will create the transaction using type ID create method. Here I am creating the transaction. TX is the handle for the sequence item. Then what it will do? It will wait for grant. It will wait for grant. This wait for grant signal is the request from the driver, requesting sequence item from the driver. So in the driver class, you can see it is requesting the get the next item. That is the request to the sequencer. Sequencer will send grant to the sequence, and our sequence will wait for that grant. Once the grant is achieved, once the grant is received, then it will randomize. tx.randomize, it will randomize the transaction and it will send that request transaction to the sequencer. That sequencer will send to the driver. This sequencer functionality is default. We are not going to write the sequencer functionality in the UVM code. So in the sequence, we have randomized and send the request and wait for item done, so to generate the next random transaction. So this wait for item done will be getting from the driver. Driver, you can see it will do this functionality and then it will say the item done from the port. This will make the sequence to again generate the next transaction. So here I am repeating this for 5 times. So it will generate 5 transactions and it will send to the driver. Then driver, what it will do? It will give that to the interface and interface will pass that to the DUT. This is how the communication of driver, sequence and sequencer happens. Now in the monitor will collect the response from the interface and it will give it to the scoreboard. So the monitor and scoreboard are connected. So the monitor scoreboard connection we have made in the environment. You can see here we have made the connection using item collected port as well as item collected export of the scoreboard. These are analysis ports. We don't have these ports available. That's why in the monitor, you can see here I have used UVM analysis port and I have created this item collected port here. UVM analysis port, it will take this transaction and it will be act as item collected port in this class. So item collected port we need to create over here using new method I have created. Similarly, in the scoreboard, you can see using UVM analysis implementation port, we need to create item collected export. This item collected export I have created using new method here. Now those two are connected in the environment. This environment makes the connection between monitor and scoreboard. Now monitor will collect all the response from the DUT and it will pass it to the scoreboard. So monitor, you can see here in the run phase of the monitor, what we need to do, at positive edge of the clock, it will sample the outputs. So it will take all the values from the interface and it will take into the transaction. So this is how the monitor will do. And then coming to the scoreboard, in the scoreboard, what we are going to do, we need to put that all into the queue. We need to have a write method, that is write function. This write function is going to use the queue that we have defined it as the DFF sequence item, that is transaction queue. This transaction queue we are going to use to push all the packets received from the monitor, and this queue will be used for the decision. This is how the scoreboard is going to work. Now let us run this code and see how the transactions are going to be generated and how we are going to see the UVM tree. So you can see here, now the simulation has got completed. So now we can see the UVM hierarchy over here. This is the UVM tree which we have generated from the end of elaboration phase. And if you come below, you can see here the clock is generated. I have just displayed the clock. It is generated in the run phase, you can see. And if you come down, it will display the report by severity. UVM info we have used 32. There is no UVM warning from our code. There is no UVM error. There is no UVM fatal. And you can see how the execution will be. This is the constructor and build phase, connect phase, all come under UVM info. If you open the EP wave, you can see the generated waveform. So here is the waveform. This gives D is equal to 1 and D is not randomized fully. Let me randomize. Let me increase this to 10 and run it again. So now you can see D is randomized. Let me take this reset to the top. I have used the constraint to keep this reset 0 always. That's why reset has not randomized throughout our simulation. And you can see input D is randomized here. Up to here input D is 1, and you can see here the output is changed to 1, and once input D becomes 0, in the next cycle the output will be changed to 0. Again here D becomes 1, the output is going high. So this is a simple code to verify the D flip-flop, and here the scoreboard code is not written completely. Let us see the scoreboard functionality and let us write the test pass fail depending on the functionality of the DUT. Let us see that in the next video. Thank you.